Let's discuss a question from machine design. It's a question from brakes. So a band brake. So let's look at how the band brake is. Most of the time you have a pulley and a band combination which is wrapped around the pulley for some angle. It depends on how much angle. Now here it is given as 270. So let's just draw that. So you have one end of the band coming like this, the other end uh, is going like this. So this is not intersecting somewhere else. So it's like this, the 270. So here you have one tension and here you have another tension, and so when you apply the brakes, these tensions get increased, these tensions get activated, and by means of friction existing between the band and the pulley, which is again connected to whatever thing you need to stop. Okay, so because of the friction existing at at the interface between the band and the pulley, you are able to stop the pulley. That is the basic concept. Okay, so now the torque, the braking torque is basically the tensions. These tensions provide the opposing torque, which resists the actual driving torque. The driving shaft is connected to this pulley, so these tensions provide an opposing torque. I mean, they act in a opposing way such that it opposes the driving moment, the driving torque. So the opposing torque is given as the maximum tension, the difference of these tensions. Okay, the maximum tension direction is the one which is opposing. Okay, so T1 minus T2 into R. I mean, basically T1 into R is because these bands are always tangential to that circular thing, and so T1 into R provides the moment of each of these tensions, and T1 into R minus T2 into R is the net effective opposing torque. So this is called as the braking torque, and the braking torque is given as 1000 Newton meter. T1 minus T2. The R is the radius of the dam, which is 250, so 0.125 meters. So we know the torque, we know the meter, so we'll get T1 minus T2, which is you can write 1000 by 0.125. 1 2. Let's cancel out this. Let's write it in a uh, T1 minus T2 by 0.125. Okay, so this is one equation. We'll come back here. The other equation is how these tensions are related. Now T1 is the maximum tension, T2 is the minimum. So T1 by T2 is related as e power mu theta. This is how the tensions are related, and this we obtain by taking only the band portion and studying the friction relation between the friction tensions T1 and T2. We get this relation. So this is from the math, and there is no friction. The tensions will be equal. Mu will be 0, e power 0 1. The T1 will be T2. So now T1. So let's get this ratio, because the first equation is not sufficient to get the maximum tension. You need to have, because there are two unknowns, so two equations. So the second equation is always relating the maximum tension by minimum tension by this e power mu. If the friction coefficient is given as 0.25, and theta is the angle of overlap in radians per second, so it is 270. So in radians it is 390s, that is 3 pi by 2. So T1 by T2 is this. So we need to get the maximum tension. So this ratio T1 by T2 is e power this. If we calculate, it comes out 3.248. So this is equation number 2. Now this we want to get the maximum tension, so eliminate T2. So T1 minus, in the first equation it is T1 by 3.248. So this together is 1000 by 0.125. So this value, if I calculate, I am getting close to 11.56 kilonewton. So this is the maximum tension. So the answer for this is D. If you look at the answer, it is D, 11.56 kilonewton. So two sets of equation, in always these kind of problems you need to use T1 by T2 is E bar mu theta, that is the must, and the other is the torque equation. Thank you.